Hello, I'm Vincent Rooyakkers, and this is Lab 3, Black Hole. In this lab, we were asked to calculate the unknown mass of a black hole with a star orbiting around it. There are several purposes for this lab. The first was to predict the mass of the object using Newton's second law. Here we're mainly focusing that the sum of the pushes and the pulls is equal to the F net, and then with F net we know that's equal to dB dt, or at least the change in momentum over time. Another purpose of this lab was to solve for the mass of an object using a law of universal gravitation. You see this mostly towards the end of my code when we were actually calculating the mass of the black hole, but here we see that the magnitude of the gravitational force is equal to at least the absolute value. With here, I just took out the negative of the equation, is equal to the gravitational constant times mass 1, which in this case could be either the star or the black hole, times the second mass over the distance between these two things squared. We then go into the third purpose, which mainly focuses on the parallel and the perpendicular components of momentum and their equivalents to the corresponding portions of the net force. We could use changes in these components of momentum to calculate the corresponding components of net force. With these, we could then solve for the other unknown component, either perpendicular or parallel. In the case of our code, it was perpendicular, with a known component and a net force that we could calculate, which was just, we're doing this at small intervals of the star's motion. We're calculating F net by finding the changes in momentum. And then we could then estimate the object's mass by calculating the mass of the black hole at each of these time steps, and then just taking an average of them to get an approximation of the mass of the black hole. Okay, so here's my code. Okay, so let's scroll down to the things that I've changed. Okay, so the first thing I changed was the mass of the star here. This was given to us in the initial conditions. For delta t, this is the amount of seconds that's in a day. Again, this was what we were told to use to calculate or at least use for our time interval. Then this is also used for iterating for the loop. While it doesn't actually iterate for the loop, it's important for calculating the momentums at each time step. So now if we scroll down to the while loops, the ones that we actually edited are down here. This is how I calculated the momentum. Momentum, again, is just mass times the velocity. So we can just multiply initial velocity by the star's mass to get its initial momentum, and the final velocity of the star, again, by the mass to get its final momentum. We can then use this to calculate the change in momentum, which is important for calculating the change in momentum with regards to change in time. And again, this is using Newton's second law. We know that the net force is equal to the change in momentum over the change in time. We use this in the calculation for the parallel component of the change in momentum with respect to change in time, as the p hat is just the direction that the momentum is going in right now. But the magnitude is the magnitude of the final momentum minus or at least the change in magnitude is the magnitude of the final momentum minus the initial, over the time step that we're doing. And this gives us our parallel component. Knowing the relationship that the parallel component and the perpendicular component is equal to the overall change in momentum over change in time, we can just subtract the parallel component from what we've already calculated for the overall net force or change in momentum with respect to change in time to get the perpendicular component, and again this just gives us our perpendicular component of the net force. Once we have this, we can just calculate the overall mass of the black hole, as this is just, again, the universal law of gravitation is the magnitude of the gravitational force is equal to the gravitational constant times the two masses over the distance squared. We can rearrange this to be the mass of the black hole, so then this would just be the magnitude of the net force times the magnitude, or at least the star's position squared over the gravitational constant divided by the star's mass. And this is how we got the mass of the black hole. But this mass is calculated at each time step for an estimation at that current point. So what I then did is, I guess down here, I appended them to a list, and after the while loop runs, I find the sum of that list, and I also find the length of that list to get the average. So going back to the actual arrows, we had to use a really low number for the arrow scale because this is such a large force. And now let's look at this code run. Notice how the arrows get larger as it gets closer to the black hole because it's moving faster, gradually faster and faster as it gets closer. And this is because the magnitudes of the change in momentum are bigger at those points. And then it slows down as it reaches the maximum distance away because the gravitational force is weaker and there's a weaker change in momentum, so it starts going slower. Then also here we can see our observed parallel, perpendicular, and overall net forces at this final point. We could calculate this at each point, but this is just what it is at its final point. And overall, we get this average mass for the black hole. This is an accurate approximation of what the unknown mass is. So going into the questions we were asked to answer, one of the first question was, would this code work for a different black hole, and would we be able to tell a difference in the motion? I'm under the assumption that the only thing changing here is the mass of the black hole, and this would cause new kinematics for the star. But since the only thing changing is the mass, and the mass wasn't a factor in the calculations of my code, we would be able to tell the difference, and we could calculate a new mass. The second question asks us to analyze the difference between F net and changes in momentum. Well, these two numbers are essentially the same quantitatively, but they do differ in what they mean conceptually. For example, F net represents the sum of pulls and pushes on an object, while changes in momentum over time represents the changes in the object's motion. Where these two connect is that it is this net force, and these pushes and pulls are what causes the changes in the object's motion, and that's why these two quantities end up being equal.